This is the last major concept that we're going to cover this fall. We are going to have another lesson on this and one final lesson where we practice with the transcendental functions, mainly natural log and e to the x with our calculator, taking derivatives and evaluating definite integrals. But this is the last major new concept that we're going to encounter this fall. So congratulations, you made it. It's been a long road, but we're there. And this last concept is called logistic growth. And it's kind of sort of a model, a mathematical model, that corrects the flaws that are inherent in the exponential model for growth. On the exponential model for growth, it's flawed in that it projects faster and faster growth indefinitely. It's just like whatever population we're talking about is just going to grow and grow and grow and grow and grow till forever. It doesn't take into account any limiting factors that might be present, such as space or resources, to support the population's unchecked growth. So these forces obviously force a slowing of the growth rate, and this gives rise to a more accurate model for population growth called logistic growth. So the logistic growth model is something we're going to talk about, and this is what the logistic growth model looks like graphically. We realize that if we're talking about the population of pretty much anything, even millions of bacteria in a petri dish, there are limiting factors to unchecked growth to that population. Here we're talking about populations of bears over years. Here we had an initial population right here, whatever that point was, and as years went by, we can see that the bear population grew and grew and grew, and somewhere around in here, not sure where, but somewhere around in here, it was still growing, but it stopped growing as fast. And then around 100 bears, it looked like it stopped growing altogether. And probably what happened, a model for this is that there was only enough space for 100 bears, or only enough food resources for 100 bears. So that's the logistic growth model. Now let's kind of talk specifically about what it looks like and how we're going to deal with it. So a population often increases exponentially in its early stages, but levels off eventually and approaches what we're going to call its carrying capacity. That is the highest number of members of the population that can be sustained given the circumstances they're living in. That's called the carrying capacity. And so the population approaches its carrying capacity because of its limited resources. If P of t is the size of the population at any time t, then the rate at which the population is changing over time acts like this. And I don't know if you recognize it or not, but that's exponential. That is exponential growth. And it acts like this only when the population is small. So if P is small, we have exponential growth going on. It says initially the growth rate is close to being a proportion of the size of the population. The relative growth rate is almost constant when the population is small. But we also need to take into consideration that what happens when the relative growth rate decreases as the population increases. So the growth of a population slows as it nears its carrying capacity. Now we'll call that carrying capacity capital K. It's what we are more likely to see on the AP exam than any other letter, but I have seen it referred to as capital M. I've seen other letters refer to the carrying capacity, so let's don't get married to capital K. But we're going to call capital K the carrying capacity, and that is the maximum population that the environment and its resources is capable of sustaining in the long run. So there are several expressions that model logistic growth or relative growth rate, but the one that we're going to encounter most often on the AP test, and really it's the simplest one because it's intuitive for us. So let's work a few examples here. This says a park can support no more than 200 deer. So that right there tells me K, big K, is 200. There are 30 deer in the park Now, so the initial population is 30. Assume a logistic growth model with the rate of growth, little k, as 0.15. Find the logistic growth model. Well, our logistic growth model is the rate of change with respect to time of the population is little k times population times the factor 1 over p minus k. All right, so our logistic growth model is dp dt equals 0.15p times 1 minus p over 200. And you say, well, you didn't use p naught. Well, p naught's not in this formula, right? The initial population does not have an effect on the rate of change of the population. All right, let's see. Finally, we'll work this example. Given the population equation dz dt, here our population is some population of z in terms of t. So dz dt equals z times the quantity 4 minus z over 100, where the initial population, z of 0, was 50. So they're asking us what is the carrying capacity? What is big K? So what we need is for this factor to be in the form of 1 minus z over big K. So we're going to have to get that 4 factored out of there. So let's do that. dz dt equals, I'm going to factor that 4 out front, and that's going to give me 1. But understand, this 4, when I distribute it back through, is going to affect this value. It's no longer 100 when I factor that 4 out. It's something else. So here's what you have to ask yourself. 4 times 1 over what is going to give you 1/100th? And that's going to be 400, right? So our carrying capacity, big K, is 400. So lots of times you're going to have to do that. Remember, this limiting factor only tells us carrying capacity when we're comparing this ratio to 1. So make sure you always look at what that value is. When is the population growing the fastest? Well, the population is always growing the fastest, always, at half the carrying capacity. Just remember that. So it's growing the fastest at 200 individuals in the population. What is the carrying capacity if the initial population were 10? Well, it's still 400. We'll see when we do some work that involves slope fields and things like that, we'll see that this does affect the slopes and all that in between the initial population and the carrying capacity, but the carrying capacity is unchanged. A higher initial population will get us to the carrying capacity faster, obviously. So this more affects time than it does carrying capacity. So what is the limit as t approaches infinity of the actual population function? Now, this is saying something. This is not saying what is the limit as t approaches infinity of the rate of change of the population. That's a completely different question. So now we're talking about the population itself. So this technically says over time, what is the population? In this context, you might say, listen, as time rocks on, what's happening to the number of individuals in this population? And as time rocks on, when we actually talk about what's happening to the members of our population, that population is going to hit carrying capacity. So carrying capacity means a lot for us in the logistic growth model. There's lots of other things that we're going to be asked, but this is enough for us to get started with a logistic growth model. Come to class next time, we'll do some homework problems, and then we're going to do one more lesson on logistic growth where we see much more kind of AP type problems. So that's it for this video.